Okay, hopefully everything is good now, but if there's still stuff in the way, feel free to let me know. And okay, awesome. So for our icebreaker today, I see Manit has said the Beatles. The Beatles are really good. I like them a lot. I listen to a lot of like older music, like classic rock and stuff. So the Beatles are definitely in that genre. But that's really great. Um, Cool. Tanisha says 21 Pilots. Okay, that's a really old one. I am surprised a lot of you still even know that band because I listened to that when I was growing up. And when I was growing up, they were considered old. But they are a pretty good band. They got a couple of good songs. So yeah, that's great. Manit says Imagine Dragons. Yeah, they're still pretty popular, I think. Got a couple of good albums out there. Yeah, they're pretty good. I would say for me, you guys probably don't know any of the bands I listen to because I listen to a lot of old ones. But I would say for me, I really like Fleetwood Mac. They are an old like pop rock band kind of. I also like Pink Floyd. They're like kind of psychedelic rock. So those are some of my favorite bands. I don't know if anyone's heard of them, but okay, awesome. Renisha says Blackpink, not that much though. I only like one of their songs. Okay, that's cool. I don't listen to a lot of Blackpink, so I don't know anything about them. But a lot of my friends do, so that's definitely cool. Tanisha says they listen to Pink Floyd. Okay, that's amazing. Pink Floyd is so great, and you guys should all listen to it because it's an awesome band. They've got some really good lyrics out there. Yeah, if you guys have any favorite artists too, that's awesome. It doesn't just have to be bands. I'd love to hear artists. Project says the Arctic Monkeys. I have a friend who loves the Arctic Monkeys, and she started taking drumming lessons to be able to drum like them, which I think is really cool. So yeah, they're definitely really good. I don't listen to them a lot, but I know they're very, very popular. Yeah, that's awesome. Anyone else got some favorite artists, bands, maybe favorite songs? That could also work. Manit says Believer from Imagine Dragons. Yeah, that one I used to listen to a lot. And then I listened to it too much. So then I stopped liking it. But it was a good song. It's a good song. Yeah. Oh, your cousin sang that one, Risha says. That's cool. That's cool. It's a hard one to sing. I feel like there is a lot going on instrumentally, so it's kind of hard to sing, but that's very impressive. And he also says Unstoppable. Yeah, that's a good one. Sia's really great. She's got some really like unique music out there, so I think she's definitely very interesting. Aditya also agrees with Imagine Dragons. Yeah, seems like we got a couple of fans here for that. That's really cool. And Project says AJR. Okay, interesting. I I'm like vaguely familiar with them. Not like I don't listen to them, but I think I've heard of them. They do a lot of I don't know what it's called, but it's like a different kind of pop, not like traditional pop. But yeah, that's pretty cool. It's pretty cool. Awesome. Anyone else got favorite artists, bands? Songs, genres, anything, anything with sounds. Does anyone listen to like non-English music? So like music in other languages. I think that's interesting. Oh, Radisha says you do. What language and what artists, what bands do you listen to? Sombi listens to other languages as well. Cool, cool. Let me know, wait, Hindi or Bengali. Okay, that's awesome. That's really cool. Tanisha says Tamil. Yeah. That's cool. Yeah, let me know what language you guys listen to. I think that's always really interesting to hear because there's so much music that's like not English. So I think it's always great to learn about that. Atar says Hindi. Cool, cool, cool. Manit says Kannada. That's awesome. I listen to a lot of French music. I like French music a lot. So that's something I'll listen to occasionally. Aditya says kind of Hindi music. Awesome. Sanvi says Telugu. Wow. It's like we got a lot of languages here. This is very cool, you guys. That's awesome. Okay. All right. I feel like we talked a lot about music and things. And this is something I could talk about for like ages. I love listening to music. So if you guys are interested, especially in like old music recs, I totally got you. Just hit me up. But on that exciting note, let's go ahead and take a look at some math. We're going to transition today. Keeping in theme with a lot of what we do in this class, we are really going to be focusing on a lot of problem solving. But we'll have some themes to kind of keep everyone in line. So last week we focused, or the week before, I wasn't here last week. The week before we focused a lot on geometry and working with geometry questions. This week we're kind of like going to transition to word problems and look at some really big algebra themes. And like I know word problems is like a vast field. Like that could literally be a whole session in and of itself. But we're going to be looking mostly at like different types of techniques and problem solving. And hopefully that'll give you like a good set of tools to use to address different kind of questions. So, okay, let's go ahead and take a look at our first warm-up question, which deals with rates. Um, and if you've taken any of our previous classes, and even in this class, I believe we talked about it, we talk a lot about rates and things. And this is kind of related to that. So see if you can solve this problem using rates. And I'll give you guys like maybe a minute or 45 seconds on this, and then we'll go forward. Yeah, I see a lot of people saying 48 minutes. For those of y'all that are still solving, please take your time. You guys still have a little bit of time left, so don't worry. Okay, I see a lot more people saying 48, which is very cool. And I actually see a hand raise as well. So Adyak, would you like to unmute and share how you got 48? Oh, there we go. I think you should be able to unmute now. Okay. Oh no. Oh, your mic is not working. Okay, no worries at all. I'm just gonna, yeah, no worries. Cool. Okay, Tanisha has their hand raised. Would you like to unmute?
Uh, so basically, 8,000 divided by 5,000 would be 1.6. And if you just multiply by the number of minutes that they can paint a 5,000 square foot wall, that would be 30 times 1.6, which is 48 minutes.
Yeah, so very nice approach. Thank you for unmuting and sharing that. So an important thing to note here is that the number of people working in both scenarios is the same. So the only thing that's changing really is like how much work they're doing. And like Tanisha points out, we can find out how much work they're doing by looking at some ratios. So if we do 8,000 divided by 5,000, we can see that the second team is doing 1.6 times more work than the first team. So that means they're going to take 1.6 times more time. And the time to complete 5,000 square feet is 30 minutes. So 1.6 times 30 is just equal to 48 minutes. And that's how we get to the answer for this question. Um, I'm gonna make this a little harder and change one of the parameters and see how you guys do with that. So let's go ahead and change this 8 into like 5. Let's say instead of 8 members painting 8,000 square feet, now there's 5 members painting 8,000 square feet. How would you approach this problem instead? Okay, I don't see answers coming in as fast as before, so that shows that this question is definitely harder. And the reason why that is because now we're not just changing one parameter, we're changing two. We're changing both the amount of work being done, or the like amount of wall that is being painted, as well as the number of people that are doing the work. So because of that, we have to be very careful in solving this question. I do see an answer from Anit that is 76.8 minutes. So we'll go ahead and check out if that is right. Oh, and Project seems to agree as well. Okay, awesome. Oh, and we actually have a hand raised. So Manit, would you like to answer this question?
So what you can do is if you remember from the last question, 8 members take 48 minutes to do an 8,000 square foot wall. So then since all of the members work at the same rate, it's basically like there's three less number members, so they work at 5/8 of the speed. So they would take 8/5 of the time. So it's 8/5 times 48, and that becomes 76.8.
Yeah. Um, did you just do? Okay, yeah, perfect, perfect. That's really good. And I really like, Minnie, how you were able to use a previous result. I think that's awesome. So kind of what we're doing here is we're accounting for, we already found out how long it would take 8 people to do 8,000 square feet. And if we look at that problem and we look at how long it takes 5 people to paint 8,000 square feet, there's only one parameter changing between these two scenarios. And the parameter that's changing is the number of people doing the work. So in this case, because you have less people doing the work, it should take more time. Specifically, because you have 5/8 of the people doing the work, it should take 8/5 more time to complete the same task. So that's why we do 48 times 8/5, and that'll get you to 768 or 76.8 minutes. Okay, awesome. All of this kind of leads up to a kind of well-known formula, and this is actually came up in one math counts book. It's like a small, tiny book released by the Art of Problem Solving. If you guys have read it, maybe you'll know it, but we kind of call this the mole problem. And the mole problem is basically you have some number of like there's some amount of work to be done, and you have m moles, so people doing some amount of work in a given amount of time at a specific rate. So that sounds like a lot, so let's write it in variable format. So the mole problem typically has a formula associated with it known as W equals M R T. And I see that Manit has also put this in chat. And yeah, that's absolutely correct. So defining each of these variables, W is our work. M is the number of moles, aka the number of workers or people or whatever that are doing the task. R is the rate, and T is the time. So if we go ahead and use this in our previous question, we can really plug in and solve for the amount of work, solve for the different variables, and go from there. And that's one way to do a problem like this. I would say the solutions that you guys presented were definitely faster, but you use the W equals MRT formula when there are two things that are changing. So if you didn't know that it took 48 minutes for 8 people to do 8,000 square feet of work, and you are only given this information with 5 members down here, then this problem would definitely be a little bit more complex. And in that case, you would use the W equals MRT formula. So that's kind of like when we use this, and essentially this is really good for when you're having two parameters changing and you need to like figure out certain rates or times and things like that. So let me know if you guys are good on that, and let me know actually if you want to do a problem that works with this specific formula, because it is important and it totally does pop up. But if you think you're good with that, we can move on. Yeah, okay. I see a thumbs up from Anit. Anyone else want to stick around, do another question, or are we good to move on? Yeah, okay. I see a lot of thumbs up. Okay, awesome. Um, Let's go ahead. So this is kind of like our warm up, kind of extending what we've learned about race in the past. So let's go ahead and now look at a different kind of very common question that is very tricky. And I will admit, these kinds of questions I really struggled with when I was doing like middle school competition math. But there's definitely some nice solutions. And if you attended some of our previous classes, you'll probably recognize questions like this, but that's totally cool because this is a tricky concept, and I think it's really worth going over multiple times. So I'll give you guys like 30 minutes, not 30 minutes, 30 seconds, maybe 45 seconds, and then we'll go ahead and take a look together. Okay, I don't see any answers yet, which is fine. This is kind of complex. So let's kind of start on this question together and we will go from there. So the way I like to do this, because I'm not told anything about the mass or anything like that, and the mass doesn't really matter for this kind of question, I'm gonna make up a mass. I'm gonna say that there's like 100 kilograms of mass. Oh, okay. I do see an answer from Shrish that says 44.4. We will check that out. Okay, so let's say I have 100 kilograms of mass. So initially, I have a solution that is 90% water. So that means I have 90 kilograms of water and I have 10 kilograms of like solid, non-water. So I'll just say solid. Okay, I have another answer from Neat. That is 10%. We'll see if that's right. Okay, awesome. So let X be how much evaporates. So remember, when something evaporates, only the water evaporates. So your solid stuff doesn't evaporate. So X is amount of water evaporating. Okay, so when this changes, what happens is we now have 90 minus X kilograms of water. But remember, like I said, solid doesn't evaporate. Solid stays the same. So that means we still have 10 kilograms of solid. Okay. And we're told after this change that the solution is 80% water. So the water amount is 90 minus X, and the total amount of the solution is 100 minus X. And you can find that in two ways. You can either add up both parts, 90 minus X plus 10, which is equal to 100 minus X, or you can recognize that because X is the only thing that's changing from the original solution, you just do 100 minus X. So that's how you get the new total. And this is equal to 0.8. So now this is a very simple linear equation to solve. So if I go ahead and multiply both sides by 100 minus X, you will get 90 minus X is equal to 0.8 times 100 minus X, which means that 90 minus X is equal to 80 minus 0.8x. And then if we go ahead and simplify that, you will find that 10 is equal to, let's see, 0.2x. And then, wait, I think I did something wrong. Okay, no, we're all good. And then x is equal to 50. because remember 0.2 is just 1/5, so that means x is equal to 50. So if we go ahead and take a look at the original question, we want to find out what percentage of the original water evaporated. So remember, the original water is 90. And we found out that 50 kilograms is what evaporated. That's what we said X was. X was the amount of water evaporating. So we have 50 divided by 90, which is equal to 55.5%. Okay, amazing. So for the person that put in 44.4, I think that Shrish, that was you. I think you were close. You just kind of mixed up what was evaporating and what wasn't. But yeah, I think you were really close. Okay, cool. And then for 10, I'm actually not sure where the 10% comes from. But if you guys are confused about why the answer is 55.5 and not 10, let me know and we can kind of work through that together. I'm going to recap this because there's a lot of important parts to this solution. So if you're confused, stick along, listen around for the second time, and see if that clears it up for you. So to start off, we've got a solution. We're only told stuff about percentages. We're not given any parameters about its mass, nothing like that. And in a scenario like that, when we have no given parameters about a specific variable, go ahead and pick a number for that variable. It makes it so much easier to deal with. You don't have to add in extra variables and letters and things. So in this case, I'm going to pick 100. I'm working with percents, and 100 is like the golden number when it comes to percents. So I'm going to say I have 100 kilograms of mass. Now, with that 100 kilograms, I'm told the very first sentence of the question says, the solution is 90% water. So that means 90% of my 100 kilograms of mass is water. So that means there are 90 kilograms of water, and the rest of the mass, which is 10 kilograms, is non-water or like solid stuff. So I'm just going to write 10 kilograms of solid. Then the next sentence tells me that some water evaporates. I'm going to define this as a variable x. So x is the amount of water that evaporates. And remember, only water evaporates. Your solid stuff doesn't evaporate. So water is the only thing that's changing right now. That's why the amount of water I'm left with after evaporation is 90 minus x. This amount of solid stays the same. It's just 10 kilograms. So then, after this evaporation process, I find out that the solution is 80% water. So if I take a look at the ratio, 90 minus x is how much water I have, and 100 minus x is the amount of solution I have left. So this is my new ratio, and this is equal to zero point 0.8 or 80%. So if I go ahead and solve, very simple algebra equation, you guys are really good at these kinds of things. I get the final linear equation that 10 is equal to 0.2x. So solve for x. X is equal to 50. I ran out of space, so I went like over here. X is equal to 50. And this is why I thought I was wrong. I was like, oh, 50 is the right answer. But you have to go back and read the question, which says the percentage of the original water that evaporated. So 50 is not our final answer. We have one more step. The original amount of water is 90, and 50 kilograms of that evaporated. So to find the percentage, we just do 50 over 90. And if you guys remember your percentage tables from previous classes, that comes out to be 55.5%. And that is actually our final answer. Okay, so for any of you guys that were confused before or like had different answers before, let me know if you still have questions now, and we can kind of go over this after class. Otherwise, let's go ahead and take a look at another similar question. Okay, I don't see anything, so I'm gonna go ahead and clear my screen. Yes, this is being recorded, so if you need to go back and check something out, you are so welcome to do that. Okay, awesome. All right, so now we're working with fruit juice, but for the most part, pretty similar questions. So I'll give you guys 45 seconds to think about this, and then we'll talk. Okay. Got a couple of answers. I'll give you guys maybe like an extra 15 seconds. So since I know like these word problems are a lot of steps, pretty involved. And then we'll kind of go from there. Okay, awesome. I see some answers, a lot more answers than before. So let's go ahead and take a look at this question. So to start off, once again, I've got some fruit juice. I'm not told how much, and it doesn't seem like it is a big deal. So I'm gonna say that I have, let's say instead of 100 kilograms, because that sounds ridiculous, let's say I just have 100 grams of fruit juice. And actually, you don't measure liquids in grams, but it's okay. Um, it's just easiest to write for abbreviations. So I have 100 grams of juice, and 95% is water. That means that there are, uh, let me clean this up. I did not think about that when writing. Okay. That means that there are 95 grams of water, which is very like not concentrated juice, but that's okay. And 5 grams of solid, aka non-water stuff. Okay, so similar to before, we're gonna let X be the amount that evaporated. And we know that after evaporation, 94% is water. So always, always, always remember water is the only thing that gets evaporated. That's not math, that's science. But water is the only thing that gets evaporated. You don't evaporate a solid. So water is the only thing that's changing here. So my new water, I have 95 minus X uh, grams of water. And remember, solid doesn't change, so I still have 5 grams of solid stuff. Okay, so now my new ratio of water is 95 minus x over 100 minus x is equal to 0.94. Because now after evaporation, I have 94% water. So if I go ahead and solve for this, I get 95 minus x is equal to 94 minus 0.94x. That means that 0.06x is equal to 1. So when you solve for that, you get that x is equal to 100 over 6. Okay, I'm going to pause here and see if anyone has any questions on this initial setup. Are we good with setting up that equation and solving it and finding the value of x? And if not, please let me know, because this is definitely a difficult concept. So if you need me to go over it, once again, that's totally okay. Okay, let's recap. So we're starting off with assuming that there are 100 grams of juice. If you don't believe that 100 grams, like the amount of juice doesn't matter, go ahead and try it with 50 grams. Go ahead and try it with like 1,000 grams or whatever, and you'll see that the answer is still the same regardless. So um, we'll start off with 100 grams of juice because it's easy to work with percentages. And with 100 grams of juice, we know that the juice is 95% water. So that means that there are 95 grams of water in 100 grams of juice. The rest of the liquid is going to be solid or like non-water stuff. So there's 5 grams of solid, like non-water stuff in the original juice product. Great. So now we know that there's some evaporation going on, some amount of water goes away, goes into the atmosphere. So we're going to let that amount equal X. And after this evaporation, we know that there is 95 minus X grams of water. And that means that this is the only thing that's changed. So the amount of solid stuff stays the same. So there's 5 grams of solid, non-water stuff. And we set up our new equation for the amount of water that we have. So The new water is 95 minus x grams, and the new amount of solution, juice, whatever, is 100 minus x grams. So this new ratio, 95 minus x divided by 100 minus x, is equal to the 94% water that is given in the question. So we say 0.94. Then we go ahead, solve like we do any linear equation, and we will get x is equal to 100 over 6. Let me know if that made more sense or if there was a specific step that was a little weird. Okay, and while I'm waiting for that, in the meantime, we are asked to find out how much water evaporated as a fraction of the addition of the original juice. So the original juice was 100 grams. So we are going to do 100 over 6, which is how much water evaporated, and divide that by the amount of original juice, which is just 100. And when we go ahead and simplify that, you will see that this is equal to 1 over 6. So that is how much water evaporated as a fraction of the juice. Okay, awesome. I don't see any questions, so let's go ahead and move on to the next section of class. Um, we are going to be looking at the topic of geometric sequences. Oh, just kidding. I do see one quick question, so let's go ahead and address that really quick. So we have someone asking how we got to 100 over 6. So I think everyone is pretty clear on how we got to this equation over here. So all we're doing now is solving that. And the way to solve that is to first get rid of the fraction. So that means multiply both sides by 100 minus x. And when you do that, you get 95 minus x on the left side. And on the right side, you get 0.94 times 100 minus x, which simplifies to 94 minus 0.94x. So that's where this initial top equation comes from. Then we isolate the x and we isolate the constants. So when we do that, we get x minus 0.94x, which becomes 0.06x, and that equals 95 minus 94, which is 1. So you get 0.06x is equal to 1. Remember, 0.06 can be expressed as 6 over 100. So 6 over 100x is equal to 1. That means that x is equal to 100 over 6. So that's where that equation, or that's where that value comes from. Okay, awesome. Let's go ahead and move on to our next topic, which, like I mentioned, was geometric sequences and series. This is something that I believe is really, really important. And you guys might think it's not important, but actually, this comes up a lot. There's a lot of formulas in like the real world that really come from like geometric series, and you'll see this in all kinds of applications. I've taken physics classes where I've seen things like simplified because of geometric series. I'm currently taking a finance course, and you see like an infinite geometric series formula in there. So it's really cool. It's definitely super duper applicable. So even if you think that you are familiar with it, it's always good to review because you're definitely going to keep seeing it in application, like math application courses in the future. Okay, so to start off, what is a geometric series? It's kind of like the counterpart to an arithmetic series. Remember, in an arithmetic series, you have a constant difference. You have a common difference. In a geometric series, you're not like constantly adding something. Now you have a common ratio because you're multiplying every previous term by the same value to get a new term. So some examples of geometric sequences include 1/2, and then 1 to the power 1/4 and then 1/8. And you'll notice that I'm not writing 1 over 4 or 1 over 8. Instead, I'm writing them in a different form. 1 over 2 squared, 1 over 3, 2 to the cube. And the reason why that is because this form makes it really, really obvious to see that the common ratio is 1/2. I'm multiplying every previous term by 1/2 to get the new term, just like Manit said in chat. Awesome. So some other geometric sequences are like uh, one. 1 over 3, negative 1 over 9, 1 over 27, negative 1 over 81, and so on. In this case, the common ratio is negative 1/3. Another one is like 1 over 4, 1 over 4 cubed, so on. Common ratio is 1 over 16, or 1 over 4 squared. Awesome. Thanks, Nviti, Aditya, Shrish. Thank you all so much for putting in some of those common ratios in chat. Cool. So, like we talked about, if you've attended our previous classes, like we talk about arithmetic series, we also have geometric series. And remember, I like to emphasize this a lot because if you ever go on to study math, people will call you out on it if you don't know the difference. A sequence is just a list of terms. A series is a sum of terms. So we are now going to look at geometric series, which is the sum of terms in a geometric sequence. So there are two types of geometric sequence, one that is finite and one that is infinite. The reason why we have an infinite geometric sequence and not an infinite arithmetic sequence is that infinite arithmetic sequences have the numbers like magnitude growing really, really big. So the sum of any infinite arithmetic sequence is either positive infinity or negative infinity. So it's kind of silly to calculate the sum of an infinite sequence. But there is a case with geometric series where it can be infinite, but you can actually calculate the sum. And the reason why that is there's like a big calculus explanation into it. So if you guys ever take calculus in high school, you'll go a little bit more depth into this. But like on the surface, like generally speaking, the reason why we can find like the sum of an infinite geometric series is because if you have a common ratio such that each of your next terms gets smaller and smaller and smaller, they start playing less and less of a role in the sum, and your sum starts to approach one number. So you can kind of find like an approximation for that number, and it's actually easier to work with infinite geometric series than it is to work with finite geometric series. So today, that's what we're going to do. We're going to look at infinite geometric series. And if you're not satisfied with my explanation of why we look at infinite geometric series and not infinite arithmetic series, wait till you take calculus. It'll make a lot more sense. Okay, awesome. And on that exciting note, let's go ahead and find the sum of this following series. Now, some of you guys have already worked on geometric series, either because you do a lot of competition math or you've just seen this before in one of our classes. So if you guys know how to do this, go ahead and put an answer. And if you don't, that's okay. We'll kind of work through finding a formula together. Okay, I see a couple answers for 1/2, which is cool. Yeah, okay, I see Mini and Adyak both say 1/2. Okay, awesome. So for this one, let's go ahead, in case you have not seen the formula before, which is totally cool, let's go ahead and derive the formula. So to start off, because this is like an infinite thing, I'm going to assign a variable to it. I'm going to say this sum is equal to s. So 1/3 plus 1/3 squared plus 1/3 cubed all the way to infinity is s. Now, what I'm going to do is I'm going to multiply s by 1/3. So I do 1/3 s, and this becomes 1/3 squared plus 1/3 cubed plus 1/3 to the fourth, and so on. Okay, that's very nice. If you guys don't see where I'm going with this, trust the process. But maybe you do see where I'm going with this because would you look at that? There are a lot of common terms, and I have two equations, and I have common terms. So to get rid of those common terms, I'm going to subtract. And when I subtract, on the left side, I get s minus 1/3 s is equal to 1/3 plus 1/3 squared minus 1/3 squared, which is 0, plus 1/3 cubed minus 1/3 cubed, which is also 0. And then I just kind of get 0 all the way to infinity, which is a really, really clean simplification. So now on the left-hand side, I have 2/3 s is equal to 1/3. And so if I go ahead and simplify and solve for s, I find that s is just equal to 1/2. which is what a lot of you guys put in chat. So really amazing work on that. And yeah, okay, so kind of to recap here, what we did was we set a variable for our infinite sum, and we kind of manipulated this variable to get a different equation that had a lot of similar terms to our first equation. And because we had a lot of similar terms, we do a very simple operation. We just subtract both equations, and we can very easily simplify that to get a very nice number. So you're sitting here and you're looking at like, wow, how can 1/3 plus 1/9 plus 1 to the 27th all the way to infinity equals something as simple as 1/2. And that is where the calculus comes into. You will actually study this in calculus. And I will note that 1/2 is not like equivalent to this. It's like more of like an approximation, but it's like so close that we say that it's equal to 1/2. So yeah, lots of like calculus adjacent things in here. I will say when I took calculus, this was very cool to see, like something I had been doing for so long. You finally understand a lot of the reasons why it happens. But obviously, that's beyond the scope of this class, so I'm going to stop talking about it. Okay, so I do see a formula in the chat, so thank you, Shirsh, for putting that in. A general way to represent the sum of an infinite geometric sequence is a divided by 1 minus r. And this literally comes from the proof that we did over here. It's just made up of variables instead of actual numbers. So if you want to see the variable proof, that's in the handout that will come out after class. Also in the handout is the proof for a finite geometric series, which I think is also important for you guys to know. Oh yeah, let's define variables really quick. So A is our first term, and R is our common ratio. Yeah, perfect. Sorry about that. Cool. So this is, oh, okay, so this is all in the handout. And if you guys want to see the finite geometric series formula, that's also in the handout. So I would check both of those out because understanding where this comes from is really important. And if you forget the formula or you're not sure what it is, if you remember how to derive it, it's really easy to come back with like just like that. Okay, cool. I'm not going to go over the finite series because it's a lot of algebra, and I think you guys will benefit more from seeing it rather than me explaining it. So please do check that out in the handout. But on a different note, let's go ahead and take a look at a word problem that kind of uses geometric series. But first, I need to clear my screen because it's very hard to write. Okay, awesome. So our question for this topic is this. We got a rubber ball bouncing, and this is a very common way to apply geometric series. So an important question for sure. So I'll give you guys like maybe a minute or so to solve this. And then we'll kind of just move on to the word problem section of class where we kind of just look at a bunch of different questions. Okay, awesome. Um, I see a lot of people saying 400. Okay, cool. All right, let's take a look. Okay, so um, Basically, in this question, you are dropping a ball from 100 feet, and every time it bounces, it kind of goes to three-fourths of the height. Um, so, for example, like after the first bounce, it goes to 75 feet, and then after the second bounce, it goes to like 75 feet times three-fourths. And this kind of goes on forever. So, we want to find the total distance the ball travels. Okay, cool. So, um, let's see. Let's kind of visualize this because there's multiple things happening. So first, the ball goes down. That's a very bad line. Okay, the ball goes down 100 feet. Then the ball goes back up to three-fourths of its height. So it goes up 75 feet. And then the ball comes back down to bounce on the ground. So that means the ball comes back down 75 feet. I know those lines aren't equal, but it's supposed to show that for the ball to bounce, it's got to go up and then down. Um, so then after it comes back down 75 feet, it once again goes up to three-fourths of that height. So whatever three-fourths of 75 feet is. And then it comes back down that same height, 75 times three-fourths. So, and it kind of just goes on like that forever. So what I see here is two infinite geometric series. The first is the one where your ball is going down, and that starts off with 100 plus 75 plus three-fourths of 75, and kind of goes on forever. The second sequence starts off with 75 and then goes 75 times three-fourths, and then kind of just goes on forever. So to find the total distance the ball travels, we have to add up both of these series. So let's go ahead and find each one individually. Remember, we said the sum of an infinite geometric series was A, the first term, divided by 1 minus r, the common ratio. So in the green sequence, the first term is 100, and the common ratio is three-fourths. So 1 minus three-fourths, which is equal to one-fourth. So this becomes 100 divided by one-fourth, which is equal to 400 feet. So that's how much the ball goes traveling down. We also have to find out how much the ball travels going up. And in this case, still an infinite geometric series, so we can still use the same formula. So our first term is 75, and once again, our common ratio is three-fourths, so this becomes 75 divided by one-fourth, which is equal to 300 feet. So the sum of both of these is how much the ball travels going up and down. So that means in total, 400 plus 300 gives us 700 feet, which is the final answer. So for those of y'all that said 400, I think you guys only considered the down distance and neglected the up distance. Which is a common pitfall in this question, so don't worry, now you know. Another way that you could do this is you could also look at yeah, so like Tanisha says, you can only, or no, not Tanisha. Shrish says you could look at like going up 100, going down 100, and then like subtracting 100. Or you can also look at it just from this blue part where they go up 75 and then down 75 and so on. That sum is 300, so you double that and then add the initial distance of 100. So that also gets you to 700. So both ways work, but the idea is you have to consider the ball going up and then the ball going down. So that's where most people make the mistake in this question. Okay, cool. Glad we resolved the issues here and we are all on the same page. If you're still a little confused, please let me know. So that way we can clarify, because this is one where there is a very big pitfall. Quick recap. Okay, let's do it. So to start off, we are dropping a rubber ball from 100 feet. So I've drawn that with a green arrow pointing downwards. It travels down 100 feet. And then every time it bounces, it goes to three-quarters of its previous height. So because it went down 100 feet, it hits the ground and it bounces back up. So it goes up 75 feet. Now, after it's hit its 75 feet maximum, it's not bouncing on anything. It just kind of comes back down. So it goes down 75 feet before it hits the ground and bounces again. And because it bounces again, it goes back up 75 times 3/4 height. And then it hits its top, not bouncing on anything, so it kind of travels back down, 75 times 3/4 of its height, hits the ground, and then that process just goes on forever and ever and ever. So to find the total distance the ball travels, we have to look at how much the ball travels going down, hitting the ground, and how much the ball travels going up, hitting its maximum height. So to do that, we have two different equations. The equation in green shows how far the ball travels going down, and the equation in blue shows how far the ball travels going up. So for the green equation, we start off with 100 feet downwards, and then 75 feet downwards, and then 3/4 of 75 feet downwards, and then so on forever because the ball bounces forever. So this is an infinite geometric series with first term 100 and common ratio 3/4. So to find the sum of an infinite geometric series, we do the first term divided by 1 minus the common ratio. So this becomes 100 divided by 1 minus 3/4, which is equal to 100 divided by 1/4, or 400 feet. We do something similar for the second geometric series, which represents the how far the ball has traveled going upwards. So it starts off with 75 and then 3/4 of 75 and so on. So you have 75 as your first term, 3/4 as your common ratio. That means that your sum is 75 divided by 1 minus 3/4, which is equal to 75 divided by 1/4, or 75 times 4, which is equal to 300. So we add up how far the ball travels going upwards and how far the ball travels going downwards to get our final answer of 400 plus 300, which is 700. That was like me totally speed running all of this. So if you need to rewatch that, please do in the recording. If you have any major questions about any steps that we did here, feel free to ask. Otherwise, we'll go ahead and move on. Okay, I don't see anything, so I'm gonna go ahead and where is it? Okay, awesome. Glad to see that it made sense. If you ever if I ever speak too fast, please do let me know because that happens more often than you'd think. Okay, cool. So now I know we have like 9 minutes, 10 minutes left, so we're kind of just can transition away from class material and look at some word problems and problem solving techniques. So to start off, here is our first question. And actually, if you attended our counting class yesterday, that was yesterday, right? Yeah, that was yesterday. Okay, then maybe this is something that you are absolutely going to crush because it is a probability question. Okay, Monique, you said 2,160. Remember the question is asking for probability, so double check that. Wait, I see two different answers in chat. I see 216 over 900, and then I see 56 over 225. And I also have a percentage of 24%. Okay, that's very interesting. Hopefully, we can figure out which one is the correct answer. So let's go ahead and take a look. First of all, we know we're working with four-digit numbers, so let's go ahead and denote each of our numbers as dashes. Okay, so whenever we're dealing with counting with restrictions, always look at the most restrictive condition first. In this case, the most restrictive thing that we are dealing with is that the number has to be odd. So that is the one that limits the most amount of possibilities for us. That's the case we handle first. So if we look at the number being odd, What determines if a number is odd is its units digit. So the units digit must be odd. That means there are five possibilities for that: 1, 3, 5, 7, and 9. So there are five possibilities for this last digit. Okay, then we look at the next digit with the most restrictions, which is the first digit. The restriction on the first digit is that it can't be zero. So we have nine total digits, but remember, there is that additional question, that additional condition where the digits are all distinct. So that means that I can't have the digit that I selected here. So instead of nine possibilities for the first digit, I only have eight. Then for the next digit, I have 10 total possibilities. There's nothing on the second digit. I can do anything I want, but I have to remember once again that all the digits are distinct. So that means my second digit can't be the number that's in the first digit or my number that's in the last digit. So instead of 10 possibilities, I have 10 minus 2 or 8 possibilities. And by similar reasoning, you might think that there are 10 possibilities for the third digit, but because I can't repeat digits and I've already used three of the 10 digits, I have 10 minus 3 equals 7 possibilities left for the middle digit. Now, I'm going to go ahead and multiply each of these values together because each possibility is related, or each possibility for each digit is kind of associated with a different possibility for each digit, meaning that all of these events are independent. So I'm going to go ahead and multiply 8 times 8 times 7 times 5 by the number of four-digit numbers there are, which is simply 9,000. So if I go ahead and simplify this, let's see, how can we simplify this? Well, we can do 8 times 7 times 4 times 10 and kind of just do 9,000 there. I got 4 times 10 because 8 times 5 is 40, so that's how I would do that. And then I can cancel out a 0. I also know that 900 goes, or 4 goes into 900 225 times. So then I should get 56 over 225 as the final answer. Okay, awesome. And let's see if that actually does simplify to 24%. It does, approximately. The question specifically asks for probability. So if you're working with probability, try to denote your answers as a fraction instead of as a percent, just typically. Okay, awesome. So that is our final answer. For those of y'all that got different answers, let me know and let me know if you don't understand why this is the right answer, or let me know if you don't understand what you did wrong. Okay, and if I don't see any questions, I'm going to go ahead and put up our final problem for the night. There's a lot more problems in this handout that we did not get to go over. So if you're interested, feel free to take a look with them as like bonus to your homework and go ahead and solve them because there are definitely some interesting questions here. Okay, so our last question for tonight, we kind of go back to the theme of arithmetic sequences, not geometric arithmetic. So yeah, there's some fun stuff going on here. I'll give you guys like maybe 30, 45 seconds to think about it, and then we'll talk. Whoops, sorry about that. Okay, I already see answers from Shrish, Manit, Arena, Adara, and Anviti, all saying 92. Okay, I love it when we're all in agreement. And also Rohan, thanks for putting that in chat. Okay, so our answer is 92. Let's go ahead and take a look, see if that's actually right. So the way I would do this, well, in this case, I see a lot of very similar terms. I don't think it's worth actually adding up both sequences or both series because of the amount of terms that are similar and also for the fact that we're looking at a difference. So if I see a lot of terms that are the same and I'm actually subtracting those terms, well, there is no way I'm going to go through all the hassle of finding out what each sum is. Instead, I'm going to do something like this. So I have my sequence y. This is equal to 12 plus 14 plus 16 all the way up to 102. And then I have my sequence x, which is equal to 10 plus 12 plus 14 plus 16 all the way up to 100. And actually what I'm going to do is I'm going to say that this is 100 plus 102. Great. So now I want to do y minus x. So now when I do y minus x, well, I have a lot of terms that cancel out. And I try to make this easy to see by aligning the terms up. So 12 and 12 cancel out, 14 and 14 cancel out, 16 and 16 cancel out, all the way up to 100 and 100. So all I'm left with is 102, that's the term over here, minus 10, which is the term over here. And that is so easy to do, way easier than adding up each of these equations together. So I get my final answer of 92. So pretty cool technique that shows the art of simplification and kind of looking at what you're dealing with instead of going into brute force bashing and solving. Okay, awesome. So that concludes our class for tonight. Like I said, there are still a lot of problems we didn't get to cover, but they will be in the handout as well as the homework and everything. So feel free to attempt those questions. And yeah, if you guys have anything for me, please feel free to let me know. Otherwise, I will see you all next week for our final class. All right, thank you all so much and have a great week. Enjoy your summer. Bye bye. Bye out there. Have a great summer.